Hey guys, it's Mike Burns. Today I'm going to talk to you about two concepts that are kind of hard to understand. The first is momentum, and the second is impulse. These two concepts are related, and we're going to figure out what they mean and also how they relate to other things such as energy and force. So first question, what is momentum? Momentum is the product of an object's mass and its velocity. You might say, who cares about the product of mass and velocity? What does this mean? Why don't we just multiply two other quantities together? Well, you'll soon see that momentum is extremely useful in that it tells us something about a particular object, right? About a certain mass. It's expressed with the letter P, and the units are Newton seconds. Newton seconds are the unit because mass, which is kilograms, and velocity, which is meters per second, gives kilograms meters per second. And newtons are kilograms meters per second squared. So when you multiply kilogram meters per second squared times seconds, you get kilogram meters per second. And thus, you get Newton seconds. Why is momentum useful? Well, let's figure out what this represents. Let's say you have a bullet and a bowling ball. Now, obviously, if one thinks about the two objects, which could do more damage to a human being? Obviously, you're going to say the bullet. But the key here is momentum. If a bullet is moving at a low velocity, it's going to have a small momentum because its mass is already small. So if you multiply a small mass times a small velocity, you're going to get a small momentum. And ultimately, it's not going to hurt very much when it hits an individual, right? If you try and throw a bullet at someone, it's not going to do a lot of damage. But then if you take a bowling ball, which has a much higher mass, and throw it at the same velocity, it really is going to do a lot of damage to whoever it hits. Of course, in the same respect, instead of changing mass, if we were to change the velocity of the two objects, or in this case specifically the bullet, and we raised that bullet's velocity to 800 meters per second, then clearly it would do a lot of damage. Of course, if someone were able to take a bowling ball, or let's say a cannonball, and put it at the same speed, it would do even more damage respectively. So as you can see, it's sort of almost like the energy that an object has, and later we'll see how momentum does relate to energy. They're certainly not the same thing, but they are very similar. Before we continue, let's quickly talk about the everyday usage versus the scientific meaning of the word momentum. Someone might say that the basketball team lost its momentum late in the game and couldn't pull it out in the fourth quarter, so they lost. Or someone might say that the temperance movement was gaining momentum in the later portion of the 19th century and had a great impact on society because of how strong it was. These concepts kind of give you an idea of what momentum is. It's like the strength that an object has in its movement, right? It connects to the concept of inertia and how an object that is in motion will stay in motion, and an object with a greater mass is going to have a greater effect whether it hits another object or how much energy it has while it's moving. So now let's move on and see if we can clarify our idea of what this means. Momentum and force. How do these two concepts relate? We already said that momentum represents Newton seconds, and we know that newtons measure force, right? So how do we connect the two? The answer is Newton's second law. Newton's second law states that the force equals the mass times the acceleration. We saw this during dynamics in that the net force of an object in a particular direction showed that if it was positive, right, the object had a positive acceleration, and the object's mass would determine what force was required to give it this acceleration, or in turn, given an acceleration and a mass to figure out the force. With a simple manipulation, we can see that F equals ma soon becomes F equals change in momentum over time. Basically, if you look at acceleration as a change in velocity over a change in time, you can then rewrite F equals ma as F equals m change in v over change in time. And we know that momentum equals mass times velocity. So, F equals mv over time, or F equals momentum over time. Therefore, we can express the two concepts as a related idea. So, as you can see, our units are also still holding up, because force, which is measured in newtons, equals momentum measured in Newton seconds over seconds. Newton seconds over seconds equals newtons. Therefore, everything's holding up. Now, what does this mean? This means that a net force is present if there's a change in momentum. So, if an object increases its velocity, right? Say you have an object with a mass m and a velocity of 3 meters per second. If the velocity of this object goes up to 6 meters per second, we can now determine that there is a net force acting on the object. Due to the fact that momentum equals mass times velocity, if velocity changes, momentum also changes. So with an increase in velocity, we have an increase in momentum. And if you think about it, connecting back, if you had a bowling ball and you're throwing it, if you then throw it with a faster speed, right, a faster velocity, this bowling ball is now going to have a greater force on impact, a greater momentum while it's moving, and it's going to have more energy, as we'll later see. It turns out that momentum and energy are also related. It's great how physics is really all interconnected. Now we'll see here that momentum and kinetic energy, as the question prompts, we can relate these two concepts. Kinetic energy, which we know equals 1/2 mass times velocity squared, can soon be converted if you do a simple little trick. If you multiply the 1/2 mv squared by 1 in the form of mass over mass, you then get mv, the quantity squared, over 2m. Now since we know that momentum equals mv, we can substitute the p in and get p squared over 2m is equal to kinetic energy. Now it's very clear through this mathematical relationship that kinetic energy connects to momentum, and that these two concepts are very similar. So the trick now is to not get confused. While an object that's in motion has kinetic energy and it has momentum, these things are not the same, but they are very similar. The two ideas are interdependent. As one goes up, the other goes up. In this regard, we can use momentum to solve problems involving energy, and vice versa. Now let's move on to a topic we mentioned earlier, impulse. What does impulse represent? Impulse represents a change in momentum. You can express it as a capital I, and it represents the average force times the change in time. So basically, this means that if we exert a certain force on an object over a period of time, right? If someone's pushing the bowling ball for 5 seconds, right, and exerting a force of 10 newtons on that bowling ball, if we multiply the 10 newtons times 5 seconds, we're going to get 50 newton seconds, or a change of 50 in our momentum, right? Which will indicate a higher velocity than our original velocity, because the masses, as you can see, will stay the same. So therefore, mvf minus mvi, this mvf term goes up, because the final velocity will now be higher as a result of a greater force. Just in terms of terminology, something exerts an impulse on an object. So it's similar to the terminology for force, in that a force is exerted on an object. Impulse in the same fashion is exerted on an object because it relates back to the concept of force as seen in the F average times time up here. So let's wrap it all up now, connecting these concepts together. An exchange of momentum or energy between two objects or between multiple objects is called a collision. Obviously, you've heard the term collision before, right? Involving maybe a car crash or any situation where two things slam into each other, football players or any other contact sport like that. And this term collision will be used in physics to represent anything where directions change, velocities change, and as a result, momentum and energy are transferred between the objects. In terms of units, right, let's wrap up again by saying that force equals newtons, momentum equals newton seconds, impulse also being measured in newton seconds, and energy in joules or newton meters. As we can see, these terms are all connected through the newtons, and basically force is going to be involved in all of them because a greater momentum will indicate a greater force is present. Likewise, greater energy means greater force, and greater momentum. They're all directly proportional, and as a result, we can use the different terms to help us solve problems in physics involving other characteristics. As we'll see, getting into problems involving momentum, with car crashes perhaps, we'll see transfers of energy and forces exerted on objects. So all these concepts are going to come together, and as we progress through physics, we're not going to leave any out. I hope you really enjoyed this presentation. I apologize for all the times that I said the word right, and have a great day. Bye.